All right, so the last class, things have gotten a little bit technical lately, and we're talking about different ways of measuring distances, and we need to continue that today. I'm trying to catch up because we missed a class, so I'm going to hopefully get part way into the next lecture today. And this is, in some sense, these two classes are about as technical as it gets in this course. So I am begging you to bear with me. This is a little bit complicated, so be sure to ask questions. It's complicated because we're really trying to assemble this map of our neighborhood, and it's not an easy thing to do because judging the distance to something very, very far away turns out to be very, very difficult. Judging things nearby tends to be difficult as well because the things that are close to us aren't always the brightest things. And so we played with this a bit last time, and we talked about a few different types of ways to measure distance, particularly these binary star systems, right? So I'm going to just call on some random people, and you're going to try to tell me something you remember about that. And even if you don't remember the details, we'll try to unpack them so that we can get back to where we're at. All right, cool. That's a great place that's something we should review for sure. So yeah, one of the big pieces of this puzzle that we need in order to understand really what we're looking at is how big the objects are. And we get that from Kepler's relationship, which is something that I think, that you will have to go over, or probably had to for last week's quiz. But your book harps on this a bit, and we talked about it last semester. But it's essentially this idea that the speed at which something goes around something heavy, right? In an orbit, let's say there's a smaller body like the Earth, and there's a larger one like the Sun. The speed that it goes around it, the orbital period, that's how long it takes, is going to be in some way proportional to how close in it is to that star, right? So the planets in our solar system, the ones that are closest to the sun go around the fastest. They have the shortest periods, so the shortest years, right? And it's not a perfect relationship. There's some proportionality between that. But Kepler, who was the first person to put this together, he wasn't sure what it was that modified that relationship because it didn't seem to hold perfectly. And Newton came along later and said, I think it's how much stuff there is in each one of those bodies, right? The mass, how much gravity, how many atoms there are, right? And so this relationship that we pull out from these orbits allows us, by looking at the center of where that orbital system is at, so if there's two bodies, they're going to orbit a central point, but it's going to be skewed towards the heavier one. And from that, you can deduce the mass contributions of the body. And eventually, by getting that, plus looking at the way that they're moving, we get a sense, we can make this rough distance calculation by setting up a triangle. And that'll make a little bit more sense when we talk about parallax today. But I'm really glad you brought that up, so thank you. And we'll go over it some more too. This is something we just can't escape. Let's see here. That's the other missing piece. So he mentions the shift, the Doppler shift that's happening. That gives us some evidence. If we know the time, right, and we know exactly the speed too from the Doppler shift, just like essentially like the police officers on the highway. Then we can deconvolve time and speed, and we can get distance. So we know the width of that orbit, which is the other part of that. So there's a lot of information that we can get out of these binary systems. Unfortunately, not all star systems are binaries, or at least binaries that we can see, and so that becomes a limiting factor. The goal at the end of this, hopefully we'll get further than this one lecture today, but the goal is to set up something which we call a cosmic distance ladder, which is the assemblage of all these different methods for assessing distance, and we can kind of compare and contrast them. Some of the methods will reach out further than others. Obviously, well, maybe not obvious to you, but we can't see pairs of stars in other galaxies. They're just too freaking far away, right? We can see the ones that are in our local neighborhood here in our galaxy, and so this spectroscopic, or let's say this binary method is great for things nearby, more or less nearby us, but it's not going to work when we get further away. And so we have to come up with some different methods that we're going to talk about today. Let's do one more. I think we've pretty much caught ourselves up from last week. How about, I think we might have mentioned that the week before, or the class before. But I think you bring up a good point, which is just, it's interesting that all we have is light, and we have colors of light, and that we can get something about the motion from the colors and how it changes. I think that's really, really important. That's going to keep cropping up over and over again. Now, that's, of course, like building a huge pyramid of assumptions underneath our feet, too, which is that all of these things behave appropriately and everything's more or less homogeneous at all points in the universe. And this is leading to no paucity of strife in the astrophysics community right now. And this is going to become more and more apparent after we move through some of these technical details, that a lot of these assumptions that we're making right now, they're either wrong or there's pieces of the puzzle missing because things don't seem to be behaving at large scale the way that we would hope that they would behave often. And so that'll become a sort of tasty piece of this story down the road. But we need to make a little bit more technical sense of it first. So let's keep going with this. For whatever reason, at this point, the textbook is going to take us back a little bit to the concept of, we're going to talk about distance, but we're going to talk about parallax, which is the most basic way that you can gauge a distance. This is what surveyors use on Earth, to lay out the groundwork, the framing for new structures, right? How do you figure out how far exactly something is away? I'm going to make this highway curve with, this many degrees of turn at this many miles. Well, how do you know exactly how far a mile is? Like, do you just walk it out? Do you have a big, long measuring tape? And obviously, that's inconvenient, and it doesn't work really well if you have to go across hills or something like that. So how do you do it? And you use this concept of parallax. And this was how people, all the way back to the Greeks, tried to figure out distances. Problem is, things are really, really far away. And so we'll see how parallax is a pretty limiting way of looking at distance. And I'm kind of surprised this wasn't the first thing that we go through in this course with the textbook, but for whatever reason it's not. But this is the most ancient way of gauging distance. And it works really well in our local neighborhood for certain stars, but it's not going to be sufficient to look outside of our galaxy. So from there, we're going to look at two additional ways of gauging distance. One is variable stars. Those are kind of interesting. These are pulsating stars, and it turns out that the way that stars pulsate is, hopefully, we believe that it is consistent based on the timing of those pulsations. So if I see a star pulsating with a certain rate, then I can more or less know the luminosity of that star, the true brightness of it. And if I know the apparent brightness, and then I can assume the true brightness, now I know the distance to it all of a sudden. That's the basic concept there. And then we're going to talk about how you can get this thing called spectroscopic parallax, which has nothing to do with parallax. Again, I apologize on behalf of all astronomers everywhere. But this is essentially saying, okay, well, I know what kind of star this is. I know roughly where it should fit on that HR diagram we developed last time. And so I should know more or less its true luminosity. And then, again, apparent luminosity to true luminosity. And we'll talk about that. So you can start to see how these assumptions are starting to pile up. And so our certainty becomes less and less the further away and the more assumptions that we have to pack into these measurements. We can't just go out and stretch a measuring tape to the nearest star. And the next best method, parallax, which we're going to talk about momentarily, turns out to be really, really difficult because, let's do a little experiment really quick. So if you put your finger in front of your face or a pencil or whatever, and you close one of your eyes, and then you close the other eye, you can see that the pencil moves back a little bit, right? So that's cool. You've essentially done a parallax experiment with this pencil in front of your eye, and I'll show you how you do this calculation in a second, but you can see a change in the two positions, right? And what you can do is you can triangulate it. This is actually how you get depth perception. It's the reason that you can navigate the world. It's really the reason why you have two eyes on your head. other than the fact that it's nice to have that redundancy. But because of this, you get a sense of distance naturally, and we do it all day long without even thinking about it. Now, the problem is, take that same experiment and move that pencil a little bit further away from you and do the same thing. The pencil, it seems to move less, and the further and further away you move it, at some point it becomes like it doesn't move at all. And so the distances to the stars are inconceivable, and we can actually, instead of having two eyeballs, we are actually able to use the two opposite positions of our planet during its orbit. So in winter and summer, let's say, or in spring and in fall, the Earth is set apart, just like your eyeballs are set apart. You have that base. It turns out, though, that the stars are so far away that the parallax becomes very, very tiny for most of these stars, and it's not appreciable. The error in measuring that parallax becomes a serious problem. Now, all of this is based on probably the most, maybe the most groundbreaking mathematical invention of all of humanity, which is this concept right here. You guys probably know it as the Pythagorean theorem. I would be shocked if you escaped high school without learning this one. But it's a really basic idea, and I don't know, it seems to have been in place in most ancient civilizations to some extent. It seems like most people have figured this out. And you can describe this, you've probably heard it as the a squared plus the b squared equals the c squared. What does that really mean? It really just means that when you set up a right triangle like this, that square, the little guy, plus the smaller one, the one on the right, the area of those is equal to the bigger area of the hypotenuse. That was the revelation. The result of this is that you can calculate the length of that hypotenuse, the longer angle on the longer side on the triangle, just by knowing the other two. Now, we're going to have to hold on to that idea for just a second, because we need to talk about what distance really is. So, does anybody have an idea of how you would define distance? Can I get anybody throw something out there? Yeah.
Getting from point A to point B.
Yeah, that's a pretty good way of looking at it. It seems to concern a path between 2 points, right? 2 locations. So distance really is what allows us to specify our place. And so when we break that out into 3 dimensions, there's really only 3 spatial dimensions, right? There's 3 places that you can be. You can be in this direction, you can be forward or backward in it, right? So you have height, width, length. And so using just 3 distance measurements, you can essentially specify your location, your place. And really location, what is that? Well, it's really just your distance to all of the other objects, all the other bodies in some physical landscape. And we can abstract that into this 3D coordinate system. But really, if we're talking physics, if we're just talking about the physical universe, all we're doing is triangulating our location based on all of the other bodies that are surrounding us. It's funny, people have been trying to come up with ways to measure distance for ages. We still are kind of divided in this country. Right? We got miles, but for science we use kilometers, which is a bit confusing. People have used everything from knuckles, right? The inch, I think, comes from like the thumb, the bottom between the 2 bottom joints on the thumb. They got like hands to measure horses with, and it's very interesting how people have just done this based on body types. What we're going to move towards is that we actually end up in astronomy measuring distances based on the angle of separation in those parallax measurements. And so we're going to talk about something called the parsec here in a little bit. The reason for that is that the distances in astronomy are just so absolutely enormous that like I think I mentioned before, if you try to imagine a million or even, try to imagine 1,000 of anything in your head, it's essentially untenable. And so the way we do it is we compare everything to the parallax that we would observe based on the seasons here on Earth, right? Setting up that baseline. But people have been using this basic trigonometric system, which is what I said, the hypotenuse-based model, the Pythagorean theorem. They've been using that forever, essentially. Last semester, we had a bit more time to talk about this. But one of the first people to figure this out was back in ancient Greece. And it's interesting because by essentially looking at this same trigonometric relationship as it applied to shadows falling on the earth, they were able to actually measure the size of the earth, right? And this is fascinating because people seem to have even forgotten that the earth was a sphere for almost 2,000 years after this. But what they essentially did was they looked at how at noon the shadow would be essentially non-existent at one point, and then on the curve of the earth, a slight shadow would appear a few, maybe 10, 20 miles away. And as a result of that, you have the baseline of this triangle here, and you can calculate the angle of the shadows here by doing the opposite interior angles, right? A little bit more geometry. You can actually gauge the angle at the center of the earth if you trace it all the way back. Anyways, you end up setting up your triangles, and you can actually gauge the distance that the entire circumference should be if you multiplied it out. If you're looking at a tiny little fraction, an arc of that circle, which you know the length of, and you know the angle, now you can set up the entire circumference of the earth. So this is really, really old technology that's been in place. And it's interesting how people keep working to set up these standards. I think standards of measurement are just one of the most bizarre things. They actually didn't create the meter until the 1700s. It was actually Napoleon who came up with this idea. He decided to define, it wasn't Napoleon himself, but it was his people, let's say, his government, his engineers. They decided to define the meter as 1/10,000,000th of the length of an arc on the surface of the Earth from the equator to the North Pole. So 1/1,000,000th of that was the definition of the meter. That's still essentially the definition we use today. Let's talk about that in a second. Napoleon's people also defined mass in terms of a liter of water, which is essentially what we use today too, which is kind of interesting. Today, actually, for the meter, we've redone it in terms of atomic clocks. I haven't had much time to talk about atomic clocks. We'll come back to them when we get to relativity. They're actually quite interesting. So this was back in 1983. The meter was actually defined in terms of how far. So light in a vacuum will travel 1 meter in exactly 1,299,792,458 seconds. Seconds, right? A small fraction of a second. And they can set up these resonating chambers, essentially, where they have atoms that are vibrating, electrically vibrating. They're pulsating, going through these transitions. And the speed at which that happens is how we actually end up getting distance, because we know that light travels at a constant speed. Now, there's problems with that. I'm not a huge fan of that conversion, because the problem is that those atomic clocks behave kind of differently depending on where they're located. They're very strange. Actually, all clocks, it turns out, seem to break down when you move them around in gravitational systems. So if you can think about it this way, if you have, anybody have one of those grandfather clocks in their house? Their parents have one or something? A couple of those? You've seen them before, at least. They have a pendulum, right? And time is kept because the gravity is pulling the pendulum, right? And you have to periodically wind them up and start them over again. Okay, that's a great way of keeping time. What happens, though, if you take that thing up into outer space? It doesn't keep time anymore, right? Well, time stops, technically, according to that clock. And a lot of the clocks that people built in the early years would kind of display this strange anomaly, this problem that we have with clocks in general, which is that most of our timekeeping systems work only in one context. And atomic clocks, it turns out, are really no different. It turns out that if you take an atomic clock up into space, well, it also seems to slow down. And it's funny because a lot of pop-sci pieces And even some like fairly high-level thinking mathematicians, they look at this and they think, oh man, I think time itself has slowed down, you know? But in all reality, like those clocks are just atoms that are vibrating. And so in some sense, you know, actually the clocks speed up in outer space, excuse me. So what's going on there? Well, if you have a bunch of atoms and they're crammed together here on Earth, they're experiencing a lot of gravitational stress from one another. They're getting pulled on by each other, right? When atoms are close to each other, they pull on each other. This is what gravity is. And so the fact that those clocks are getting stressed when they're on Earth and slowing down, it shouldn't be completely surprising to us. But people have spooky interpretations, so. All right, so that's distance for you. There's, you know, there's another way we can do distance calculations. This one probably won't come up too often, but we can use radio telescopes actually. And what we do is you often see when you look at these pictures of these radio telescopes that there's often many of them and they're separated out. You guys may have seen these fields, like the SETI fields or something like that. It's huge radio telescope arrays. And they're spaced out by like pretty serious distances, sometimes orders of miles. And what's going on with that? Well, what they're actually doing is they're looking at how long it takes for one phase of light. Remember, light has phases to it. It has peaks and troughs, right? It's a wave in some sense. It propagates as a wave, and so the waves can interfere with one another, right? If one of these telescopes gets hit with a peak while the other one gets hit with a trough, then you can get some sense of the actual radiation points of those as well, because you know where it's coming from. And so by setting up a baseline, again, you set up that triangle and you can get the distance to some of these stars as a result of it. Now, this is, I guess we'll hold on to this for a minute, because I really want to make sure, I probably should have done this first, that we have a really good grip on this parallax idea, because it comes up over and over. Yeah?
I'm a little confused as to the process of the radar and
Yeah, let's come back. I put those slides in the wrong order. I'm sorry about that. Let's come back to it after we talk about parallax and see if it makes sense after that. So it's really just a special case of this exact same system that I've shown up here. So this is what surveyors use, right? And the goal is to set up two right triangles here, right? So by setting up a baseline and measuring the angle between these 2 points, you can actually set up these two right triangles. And if you know the baseline and you know the angle, then you can calculate using basic trigonometry, right? These are the sine-cosine relationships that we were all beaten to death with in high school. We can calculate the length of that hypotenuse, right? Now, the further away something is, the bigger baseline that we need, it turns out. And that's what becomes super problematic. So to answer your question, when you're talking about, let's see if we can go back to that. When we're talking about interferometry, which is what this is called, what we're actually doing is we're setting up a baseline. We're looking at we measure, in some sense, when this light wave is arriving. We know the speed of light, right? And we know how it is affecting each one of these points differently, and we can draw a triangle between the two of them. And because of that, we can pull out the actual distance to that star. So we have a difference in how long it takes from one to reach the other, and we get some sense of the size of that triangle from that difference. This is a method that I don't think that your textbook even mentions. I just thought I would throw it in here because people do use it, but it's not one of the more popular methods for distance. All right, let's keep going with the parallax, and maybe this will make more sense. Here's another way of looking at it. Okay. So this is like setting up the biggest baseline that we can really imagine in our solar system, right? We measure the position that a star looks, just like the surveyor, on one side of our orbit, say at point A. And you get down here is what it looks like from point A, right, in the sky. Then we wait until the other 6 months later, and we measure it from over here, and the stars appear to have shifted a little bit, right? Well, from the change in position of those, we can draw a similar triangle. Remember, opposite interior angles for these lines are always the same, right? So we can know the interior angle here as well. And that angle right there, which is P in this equation, it allows us to back calculate the distance to the intersection of those points, which is really where the star is actually located, the average of the two, right? That's what your eyeballs are doing all the time, is they're averaging the two distances that it perceives, the two locations. That's how you get depth perception. So 1 over that angle, that parallax separation angle, assuming the baseline of 1 astronomical unit, so that's half the total baseline, right? We're setting up, we need to set up right angle triangles, right? Assuming half that is 1 astronomical unit, the amount to the Earth, we can actually start to get a definition for this distance unit that we're going to keep using throughout the course. So the question is, how far would a star have to be in order to have 1 arcsecond of parallax in this system? So what's an arcsecond, by the way, of parallax? Well, an arcsecond is an angle, right? It's a second, so it's 1/60th of an arc minute, and there's 60 minutes in an hour, and there are 300, well, there's 60, there's 60 minutes in a degree, and there's 360 degrees in a circle. And so these are really, really tiny. It's something like a millionth of a degree of a circle, right? Is a tiny window. And so the question becomes, with that amount, a millionth of a degree of separation in the sky, so you're really just seeing the tiniest, tiniest fraction, how far away is that star with the baseline of the entire orbit of the Earth? And the answer is about 3.5 light years, 3.26 light years. That unit right there is called a parsec. So you probably encountered the concept of parsecs. They use it in Star Wars and Star Trek, but it's also how we measure the distance. In addition to light years, people will list things in terms of parsecs because that's the way that they actually measure them, especially in the earlier days. So when you hear the word parsec, you can think that comes from parallax, and it amounts to a number of light years away. Now, how far away, by the way, is 3.26 light years? Anybody? Is it far enough to get to a star? Not quite. No. Yeah. So the nearest star is maybe 4 or 5 light years away. So almost 2 parsecs. So this is it's a huge distance, but it's not big enough to even really get anywhere. Okay. That's just another way of looking at it. All right. Now, people were unable to actually, these distances, these parallaxes are so small that people actually didn't believe they could be measured at all for most of human history. They certainly can't be seen with the naked eye. And so once telescopes started to really become high-tech, we were able to finally start to resolve some of these. So the first satellite that was really appreciably able to measure serious parallaxes, this is, again, between the two, this huge baseline even, between the Earth at its different points in its orbit, was called the Hipparcos satellite. That was in '89. And it was only able to measure a few, thousands of stars out to a distance of about 300 light years. Okay? So they've improved this recently. There was another satellite launched in 2013 called Gaia. This one measured something like 1 billion stars, and it was in the neighborhood of 30,000 light years from us, which might seem really far, but it's actually not that far. So does anybody have any idea of how far the nearest galaxy is to us? What's that? You got a guess?
Millions?
Yeah, it's in the order of a couple million light years away, right? And those are the kind of dwarfy galaxies that are really nearby. So galaxies are millions to tens of millions of light years away from us. And so 30,000 light years might seem really good, but this method's pretty limited, right? If the best we can do with our modern technology is 30,000 light years away with this, that's not great. By the way, I think we talked a little bit, maybe it was last semester, about these Lagrange points, right? So in any gravitational system, it turns out that you have a nice little pocket on either side of the two bodies where you can park something and it'll just stay put. So these are called the Lagrange points, and they're just essentially anomalies. They're little balance points in the gravitational pull of each system. And so the really nice thing is that these satellites, when I'm talking about Hipparcos and Gaia, they park them at L2, which is opposite the sun, so they don't get the sun, all the sun's light bleeding into them and so forth. And they can just kind of travel with us as we make our way around the solar system, which is pretty cool. Okay, let's talk about using this variable star method. This is pretty interesting. Okay, and here the assumptions begin to pile up in full. So, there was a lady working, I believe, at the Harvard Observatory in the early 1920s, and I can't remember her name. I'm really sorry. I apologize, Venerable One. She began to study these pulsating stars, and she noticed essentially that there was a relationship between how fast they pulsated and how bright they were. And, you know, brightness is, of course, a sort of tricky, it can really lead us astray because, you know, you don't know if that headlight that's coming at you is just really dim or if it's far away in some sense, right? It's very hard to deconvolve the two. But what she found was that all of the ones that were pulsating in a particular location, so I think she was looking at the Magellan Cloud at the time, she was like, all right, all of these guys are essentially in the same place because they're all in this Magellan Cloud. And there seems to be this really definite relationship between how bright they are and how fast they're pulsating. And as a result of that, since through other methods, some of these other methods we've talked about, they knew the distance to the Magellan Cloud, they were able to set up a ruler, essentially, where they were able to say, hey, if there's a type of star that's pulsating at this rate, and we know the distance to that based on the Magellan Cloud, then anywhere we see this thing, like in other galaxies, right? If we see something pulsating with that same rate, then it must be able to be scaled based on the Magellanic distances, essentially, right? So if it's some fraction of the brightness, but it has the same pulsating, then we can scale it based on the known distance that we have. And this was the concept of Cepheid variables. They're called Cepheid because they're in this constellation. There's another type called RR Lyrae, which are a similar group of stars. They just have slightly different pulsation characteristics. So there's these two types. And you'll hear this over and over again, is that they call these things standard candles, right? Because they know how bright that thing is. It's like if you saw a particular LED, right, and it was only manufactured by one company, wherever it was at in the world, if you could see how bright it was, you would know how bright it truly was, and therefore you could gauge the distance to it. And that's essentially how these work. So what they do is they measure the apparent brightness, the magnitude, apparent magnitude. They measure it versus time, and they can see, by the way, these things are pulsating on a really fast scale. And we don't have, you know, it's not a ton of time right now. We're going to talk about the lives and deaths of stars very soon once we make this map up of our neighborhood. But this is thought to be a particular moment in the death of a star, actually, as it's and a lot of things change about this star as it's going through this. In particular, it's the color of it changes as it's pulsating. The size of it changes actually as well. So by looking at the spectral lines, you can actually see Doppler shifts as the surface is moving towards you and away from you. So the stars are actually breathing and expanding, right, like this. And something crazy is going on, and I think we'll have a bit more time to talk about it when we talk about the end stage of giant stars. Yeah, let's get to that more later. But needless to say, they swell essentially. There's some interesting heating and cooling effects going on, but I think it'll make more sense to talk when we talk about the way that stars die, to talk about these pulsating stars. But needless to say, all these stars in the main sequence seem to do this very similarly. Most of the Cephids were first detailed out here, actually, in this. They got the name Cephid because they were detailed in this constellation looking towards the center of the galaxy out here, this Delta Cephei area. And it turns out that they all essentially fit into a particular region of the HR diagram. And this is going to start to make a lot more sense. We're going to keep coming back to this because this HR diagram is thought to teach us about the lives and deaths of these stars. So as you might recall, most of the stars fit onto this S-shaped curve, which is barely visible here. And then we have these giant stars that are out here in the upper right-hand corner, and these little tiny stars, these dwarf stars, white dwarfs down in the bottom left. And it's thought that as the stars evolve, they make their way towards the giant stars. They wander off the main sequence, is what they would say. And that's where we find these pulsating stars, right? So it's some transition phase as it's starting to become a giant star, is what we think. And there's much more to say about that when we talk about giant stars. Okay. Needless to say, these things make great standard candles. I'm going to skip this. I'll skip this too. I really want to make sure that we get caught up to this week. Okay. Now, the hope, of course, is that we can plot these on a line. Each one of these has a definite relationship between its period and its true luminosity. Now, that's a huge assumption, of course. We don't actually know whether it's true or not. We seem to hope that these particular pulsation periods, in fact, do always represent the same level of brightness at each stage, depending on where it's located. But could its local neighborhood influence it? Yeah, it probably could. Could the metallicity of the star influence it? There's been a number of papers recently talking about the actual composition of the star, which could change, which could alter its pulsation period, which might give you false information about the luminosity. So it's not great. And actually, the further that we get down the rabbit hole with reaching out further and further and estimating these distances, the more room there is for us to be catastrophically wrong, too. So who knows if these things will hold up in the long run. The final way that we actually use to gauge distances is called spectroscopic parallax, which, again, has absolutely nothing to do with parallax. I have no idea why they use the word parallax for this. But it essentially means you look at a star, you look at the color of the star from its spectra, and you place it on the HR diagram on the main sequence where you think it should belong based on its color, right? Based on its temperature. This is temperature versus luminosity. Well, once you place it on the temperature scale, then you should be able to pull out the luminosity from it. Again, like, what other factors could be misleading you? Well, you have some stars, right? We call them white dwarfs, but they're very hot, but they're not very luminous, right? So how do you know that you're not mistaking something for a white dwarf? Again, we have some stars that are also very cool, but super luminous. We call those giant stars, red giants and so forth. So how do you know that you're not mistaking it for one of those too? So things start to get a little bit sketchier here. You're going to be right most of the time because most of the stars are on the main sequence, right? So it's a pretty good guess if you're a gambling person, but it's unfortunately subject to the assumption that you're staring at the right type of star. And there's ways to look at the atmosphere, right, of the star, get those line spectra, and really have more and more confidence that you're looking at the right type of star. But there's still a little bit of wiggle room there. So let's review all of these again. We have trigonometric parallax of all different kinds. The types of binary star distances that we were talking about last time are, in a sense, also a type of trigonometric parallax, right? Because in the case of the parallax we've been talking about today, the Earth in its orbit is the base of the isosceles triangle that gets chopped in half, and you get two of these right triangles from them. In the case of the binary stars we were talking about last time, No, it was last week. You're actually looking at the triangle in reverse where the orbiting binaries set up the baseline, right? And so they're both very similar trigonometric methods, right? This parallax and this binary that we've been talking about. And these are in some sense the most reliable methods as well, but they also only seem to work out to about 30,000 light years because the precision with which you can even see the change beyond that just falls off precipitously. Next, we have these standard candles, right? The Lyrae and the Cephids. It seems like the Cephids are actually getting us much, oh, no, not further. Oh, 60 million versus 300,000, okay. So the Cephids are more reliable out to a further distance, presumably because they're brighter. And then we have the HR diagram, which is our biggest and most distant means of looking at these things. Now, this is the HR diagram and the spectroscopic parallaxes, assuming that you can even get the spectra of these stars in the first place, which turns out to be, it's like I said, it's very difficult to pick out a single star from another galaxy. And so you're left with these standard candles, right? Now, there's some other methods that we actually use, too, when we get really far out. And this we'll talk about nova and supernova soon, too. There's something about the timing of the way that a supernova goes down that can give us some idea of, well, if the supernova in that distant galaxy is anything like the supernovas in our galaxy, then the timing of how the events unfold should give us a sense of how far away that thing is, because we know its brightness all of a sudden, right? And we're like, well, that's the same supernova that I saw over here. I know how far that is. I know how far that appears to be based on its apparent brightness, and I can scale it. Again, do supernovas actually unfold the same way in every single galaxy, in every part of the galaxy even? I don't know. It seems to be, it's another order of assumptions that becomes problematic. So all of this is leading to a story that we're really, really working towards telling about the lives and deaths of stars. And a big part of that is, of course, setting up the local neighborhood and seeing how they're changing over time and fitting them into the story. And building out that HR diagram, I know it was a little bit painful, but it's the best roadmap we have for how stars live and die. And so I think that is probably the most painful part of this course, is all of this technical distance measurement and so forth that we've gone through. It's unavoidable, though, unfortunately, because otherwise I can tell you how far away things are, and I can tell you how certain we feel about them, but it's difficult for you to understand why. But hopefully you can see that this entire chain, this distance ladder, it gets worse the further we get away. And it's all built on various assumptions that also may end up requiring revision or attention in the future as well. There's things about these measurements that might change. If we discover that we're actually looking at two different types of pulsating stars instead of one, right? If we're looking at two different kinds of supernovas that we didn't even know about before, maybe that will change our distance estimates and the maps will change as the result of it. Okay, does anybody have any questions about distance measurement? Because I'm going to move on to stellar building blocks now. Yes?
How does it changes from measuring distances to stars to galaxies?
Like if you want to look two galaxies?
Yeah, if you wanted to get the distance from our galaxy to another galaxy.
Well, you could get the distance to each one of those galaxies and set up the two different angles on your isosceles triangle, and then you could get the angle, subtend the angle between the two of them, and you could back calculate the baseline from that, I suppose. It's all really, really basic trigonometric math, actually. It's kind of like astounding, because you think astrophysicists are these brilliant mathematicians, but this is like high school level trigonometry. It's a really, I think it's the only kind of math that most people will ever use in their daily lives. Even if you're like a construction worker, it's all trigonometry. It's just a really, really incredible invention, actually. And it seems to have been invented over and over again by different peoples, right? It's a basic relationship that everybody figured out in order to set up these incredible megalithic structures all over the world. Cool stuff. Any other questions? We'll review one more time at the beginning of class some of this, but again, it's not even totally necessary that you guys move out into the world and remember the details of this, but I do want you to understand that distance is extremely difficult to calculate, and there's a lot of different overlapping methods, and none of them are perfect. So that's the best we have. That's where we're at. Okay, so that catches us up to where we're supposed to be this week, where we're going to start talking about stellar building blocks, right? So what is the stuff that's out there before you have a star, right? What's floating around in between the stars, in between the solar systems? What do we have to make a star out of? It's actually a much deeper question than it sounds like, because a lot of this stuff is invisible, right? So, you can see grains of dust. Actually, here's one. Have a look at it. I think that scale bar is a micron, right? Which is about the length of a bacteria. So they're pretty chunky pieces of material. So there's a lot of that. And of course, light's going to scatter off that, or it's going to get absorbed by that dust. There's things you can see like that. And of course, some atoms get really excited by incoming light, and they're going to give off more light as a result of it. So you can get ionization, and that means we can see some of that gas. But a lot of the gas is just kind of cold and neutral, and it doesn't do this. It's not ionized in the way that we need for, say, these fluorescent lights to actually give us light, right? There's not enough electricity running through them. They're not luminous. A huge portion of the material out there, and people knew this before they figured out a way to detect this, was just neutral hydrogen. They knew from the mass that there should be much more stuff there than they could see. There's actually a kind of similar problem right now with this concept of dark matter too. It's like there seems to be more stuff there than we can see, and nobody knows what to make of it. And even using all of our advanced spectroscopic methods, we still can't detect any stuff there. And this was the case for neutral hydrogen for a while as well. So finding the little bits of things that we go and try to make a star or a solar system out of turned out to be pretty difficult to pull off. That stuff, the collection of all those little building blocks, is called the interstellar medium. And so we're going to spend a bit of time looking at all the components of the interstellar medium. The next thing we have to do is talk about ionization. I know we've briefly touched on ionization. I want to go through it one more time, because it turns out that the way that you can see neutral hydrogen has to do with this weird spin flip process that the atoms, those hydrogen atoms, undergo. And it's not quite the same as ionization, but I think that it'll help us to understand what's going on and how people were able to finally detect this missing material. Maybe it'll even give us insight into how we make sense of dark matter in the future. And then we're going to talk about cosmic rays, and stardust cycles, right? So it turns out there's just like, maybe you guys have heard of like the energy cycle, let's say. There's sunlight that comes in, and all these plants grow up. Somebody eats the plants. We eat the somebody who ate the plants. There's this whole like circle, right? There's a very similar circle of recycling and input energy and output and so forth with regard to the basic building blocks of stars. It turns out our star, the sun, is it's made out of a lot of leftovers from other stars. In fact, it seems like our star is probably at least a third generation star. In other words, there's been at least one star that was made out of little, let's say, basic building blocks, like just hydrogen, right? But that star went through its lifetime, was destroyed, and then its biggest pieces were taken up and incorporated into our solar system, into a previous solar system. That one got destroyed, lived its whole life, and then this one came along. The reason we think that is because a lot of the stuff that's in our solar system, even stuff like iron, is way too big for our sun to have fused it, right? Our sun's barely fusing helium, right? It's very, and we'll talk about when a star dies, there's a potential for some slightly bigger elements to get made, some maybe carbons and oxygens, but iron, forget about it, not with a star like that. So all this stuff must have come from other bigger stars that fused all these big elements. And this is part of a huge cycle, and we're going to talk about this is kind of what we're working up towards. And then if we have a little bit of time, we're going to talk about some mythology about how ancient people saw the stars. All right, so the interstellar building blocks seem to be concentrated into these huge clouds, and we got a picture of one up here. They're called nebula. They've come up before. So these are people have been noticing these nebula for a long time. Originally, they mistook galaxies as nebula. They thought that some of these nebula, well, they called them nebula, but they turned out to be entire galaxies. They were just very far away. And the most abundant gas in these things is hydrogen and helium, just like stars, just like these main sequence stars, like our star. The funny thing is, despite there being enormous quantities of these gases out there in these nebula, they're really, really thinned out. So there's something like 1 atom per cubic centimeter. So think about that. Like a centimeter of empty space with 1 atom in it, right? But they're interacting, right? They're clearly, in many cases, there's a lot of ionization, so there's conduction going between these atoms, right? And so we really have to start to think about what it's like to be an atom without any gravitational pressure, right? So all the atoms here on Earth are pretty squished down, right? When I was talking about the atomic clocks earlier, they're all pretty crunched onto each other, right? But what happens to an atom when it's completely depressurized, right? Something very interesting happens, actually. So we can build these things called vacuum tubes on Earth, right? And the funny thing about vacuum tubes is you have just a few atoms in there. They're not actually vacuums. We've never actually built a vacuum anywhere even approximating the vacuums of outer space. But they do have very few atoms, almost similar to this interstellar medium. And something really interesting happens is that the formerly neutral atoms that were in there, right, they usually got some sort of like inert gas inside of them. They become conductive all of a sudden. So it's almost like those atoms are able to hold a conversation with each other. They're almost able to remain in contact when they're depressurized like that. So the way I like to think about ionization is it's almost like you've taken all of the weight off of the shell of that atom, and it's kind of relaxed, and it's kind of expanded, right? And so those atoms are actually able to bump up against each other and interact electrically, which is, from a chemical standpoint, electrical interactions are shell-on-shell interactions between the atoms. Those atoms are so depressurized that they almost become, let's say, rarefied, undense, right? They're big. So when I say there's 1 atom per cubic centimeter, I don't necessarily mean there's just a little ball knocking around inside of a cubic centimeter. It might be that those atoms are genuinely swelled up to the size to fill that cubic centimeter. And that's a really interesting way of looking at it that I think is how it's a very rational way of looking at what's going on during ionization. So the thing is, despite it being very, very, it's the opposite of dense, rarefied. Does that work for you guys? Does anybody have a better word than that? Okay. So despite it being very, what's that? Loose, yeah. Despite it being very loose and rarefied, the atoms tend to clump together, which is quite interesting in some places, right? That's how we get these really interesting kind of strings and so forth. Now, what's interesting is that most of the last 100 years of astrophysical and stellar formation science and planetary formation, they treat this clumpiness as a gravitational product alone, right? They say, well, it's true that it's very, very low density out there, but there's so many atoms across, huge, huge swaths of distance that as a whole, there's a lot of heft there. There's a good deal of mass in all of these atoms, which is true. Now, the problem is, though, that gravity falls off with an inverse square law, right? So it's like the effect that Neptune has on me right now is like, there's not even a word for it. It's like, 10 to the 10th times as weak as Earth is on me right now, right? So gravity is really, really kind of useless at a distance, really at even a moderate distance away from something. Even from something huge like the Earth. You don't have to go that far before you're not really feeling the Earth anymore, right? And this is very evident for astronauts and so forth. I guess astronauts in orbit's a different picture, but on the way to the moon, for instance, you're not really feeling the Earth anymore. So I've always been troubled by this idea that this organization of these filaments and structures is a purely gravitational phenomena. And I think it's becoming more and more, and the more astrophysicists and planetary scientists I talk to, the more they're considering chemistry, right? That these are cooling reactions, just like this, this has been this wonderful, I went out to the Rogue River yesterday, and it was just this incredible atmospheric phenomena where there's this warm air, I think it's coming in from Hawaii right now, and it's crashing into the Rogue Valley, which is cold, the river's cold, and you get this condensation, right? This thick fog, and it's really beautiful. But you have to imagine that these very similar kind of processes must be happening out there in interstellar space as well, right? So condensation reactions are a very, very common reaction in terms of the formation of structured gases here on Earth, which is really what clouds and, there's ice crystals, right? There's little dust grains in clouds. They're very, very similar. So I think that it's not unreasonable to think about the formation of some of these nebula in similar light to these clouds here on Earth. It's a very parallel process in some sense. Of course, once you start to get a bunch of material in one place, then it can start to gravitate, self-gravitate. That's the hope anyways. Okay, so what's really interesting is there's a lot of these dust grains. I showed you a picture of one of them earlier. And the dust grains are really interesting because they're very similar in some sense to the nucleating pieces of clouds here on Earth. Right, so they're like little silicate, little sandy things almost. They have little mantles of ices, water, methane, ammonia, right? They're almost like little baby planets or something, which is quite fascinating, but also very similar to the seeds of clouds here on Earth. And so a lot of those are thought to be remnants of supernova and of other pieces of things that have already broken up before. But it gives you the impression that this has been going on for a very long time, that we're not looking at the first appearance of a lot of these objects. It's very difficult to imagine building a star without being able to seed a nebula like this. And it's very difficult to imagine seeding a nebula without some grains of sand, without some nuclei to actually start the process congealing, right? Without some chemical reactions occurring. And so it's very hard to trace back at the beginning of this, which is what we're headed towards in putting together a cosmological story. All right. Let's see. Now, one of the most noticeable colors that you'll see in these nebulae is this beautiful red color. The color red actually is traced to a particular emission line of hydrogen called the Balmer series. So what is that? It's time for us to pause for a second and talk about how atoms work again, which is, of course, my favorite subject. But I don't think you can make sense of any of this business with light without understanding atoms a bit. So this is a schematic of the atom, right? The atom, this is a basic hydrogen atom, let's say. It has different energy states to it. What does that mean? Like, what the heck is an energy state? Remember, energy means material in motion. So if you have more energy, then you got more material in motion. Now, presumably, with an atom, you're not changing the amount of material, right? So the only thing you're changing when you jump energy states in an atom is the motion. So it's vibrating differently, right? It's jiggling differently. And you can calculate actually the different shapes of these vibrations. If you take a sphere and you vibrate it, you pulsate it, well, as you do that and you add more and more energy into it, it actually starts to take on different shapes. It's going to deform in different ways. And the result of that is you get what we end up calling atomic orbitals in chemistry, right? You end up getting these different lobes on the atom that turn out to be capable of interacting with other atoms, and you can build up all sorts of crazy chemicals and structures. All of that is the result of different vibrational modes of the atom itself. So there's material that, say, this hydrogen atom and all hydrogen atoms, they have a certain amount of material. The only thing that differs across their lifetime as a hydrogen atom is how that material is undulating, quite simply. How is that material moving? And so what's really interesting is that there seem to be stable patterns of vibration. So hydrogen can vibrate at this rate, it can vibrate at this rate, it can vibrate at this rate, but it can't really vibrate anywhere in between. And this is really getting at the root of the concept of quantum and where that word quantum comes from. There seems to be these discrete configurations of energy for these atoms. What's really interesting is that as the atom transitions between different energy states, it gives off light, or it absorbs light. In fact, the only way it transitions, well, not the only way, but one of the main ways that it becomes excited in the first place is by receiving light from another atom. So, all this to say that during each one of these transitions, you get a different color of light. And that gives us information about how energized the atoms are, and we can know exactly what state each one of these nebula is at any given moment. And we can get a sense of how much radiation it's receiving, all sorts of interesting stuff. So this is the basic, there's all these different transitions, right? And the Balmer is a number of different reddish lights, although there's a few others. Actually, I'm going to jump ahead like 2 slides to show you. This is a picture, actually, if you take a prism and split up that red light, that beautiful Balmer light, you get all these different colors. And so there are different transitions happening all the time inside of this gas. That's what's quite interesting, is that the hydrogen appears to be having a number of different overtones all at once, right? It's like maybe one atom is vibrating in one way, the next one's vibrating in the other way, but there's like an assemblage of all of these different vibrations happening inside of the same gas, right? It's getting the same current through this lamp right now, but it has all of these different oscillations to it. The details of that are a bit squishy, so I'll come back. We'll get there in a second. All right, so this process, by the way, of changing between these energy states, when any gas really, but a hydrogen, in our case, since most of the universe is made out of hydrogen, we're always talking about hydrogen. It's also the simplest atom, right? It's only got 1 electron, right? It's very simple. As it gets into a higher energy state, we would say that it's become ionized, right? And so I kind of like, even though this is, just a basic roadmap of how the energy states work, I kind of like that when it's in the higher energy state, according to this model, which is basically, this, by the way, is called the Bohr model of the atom, essentially. The shell does seem to be expanded when it's in that highest ionization state, right? Just the way that it's drawn out. And so I think that in general, your textbook's going to talk about ionization as being a hydrogen who's sort of lost its electron, and like, where'd my electron go, right? But the reality of that is that it seems more, the truth of the matter is that you can model a metal the same way, right? So it's totally reasonable in the physics community to treat a metal as being a degenerate electron gas, where the electrons are spread out throughout the metal, right? Very similar in a plasma, right? It seems like, and you don't look at a metal and think, okay, this thing's like a gas or something, right? So it's not quite the right way to look at it. And you don't think about a bunch of electrons just running around everywhere, being lost from their actual atom. The truth of it is probably, I think, a much more reasonable way, let's say, to look at this ionization process is that the shells of those atoms are all blended up together, right? It's almost like you have a super atom inside of metals and inside of ionized gases and so forth. It's like their outer surfaces kind of melt with one another. So when this guy turns this way, the next guy also turns that way, right? So they kind of fuse up, their shells at least fuse up, not their nuclei necessarily. They maintain their nuclear locations. Okay, so I think that's a better way of looking at it than these electron little bowling balls just like flopping off of the atom and flying away. This is a schematic way of looking, but I don't think that it's physically tenable. What's that?
Is it thundering outside?
I have no windows to answer yes or no to that. It does kind of sound like it, though. Might be just the air sense. I have no idea. Okay. By the way, so there's also this other interesting process that happens. So inside of like these lights that are above our head right now, there's a voltage being applied to the gas inside of these lights, right? And it's giving, as a result of it, they're getting excited, they're getting ionized, they're excited into a new state, and as they relax, they give off light. But actually, the light that's given off by that excitation is in the ultraviolet range. We can't actually see it in these lights right now. So there's a lot of ultraviolet light being given off. What happens is that these lights are coated in another substance, which when hit with that ultraviolet light, gives off another color, which is of a different wavelength. That process is called fluorescence. That sort of thing can be happening all of the time inside of these nebula as well, right? So ultraviolet is very, let's say, it's very close to the peak of a lot of these star systems. So our sun, for instance, gives off a ton of ultraviolet light. There's a lot of ultraviolet light, in other words, flying around in the interstellar space. But what it does is it interacts with these clouds. It excites them. It kicks them into different configurations. And some of these, some of the different actual condensed atoms in those can fluoresce in a similar way. And so we have not just the direct light from the ionization to contend with, but we also have indirect light, which is from atoms getting re-excited by ultraviolet light. Similar kind of process. All right. Now, like I said, we can look into these clouds and we can see, how some star, maybe as it passes behind a cloud, it's going to give off new absorption lines, right? So there's gases in there. And we can see, since these new lines appear, we can say, okay, well, there's these chemicals in there that are clearly absorbing at those particular frequencies. And that's all well and good. Problem is, some of these clouds, like I said, tend to be neutral, right? They don't absorb light, in other words. Or if they do, they relay it pristinely without actually getting ionized into a new excitation state. And so this became a huge trouble about how in the world we would actually go about detecting this neutral hydrogen stuff. And the key to that was actually discovered not until like around 1945. There was this student, this Dutch astronomer actually, he was still a grad student at the time, named De Holst, and he was playing around with he was studying some of the quantum mechanical equations concerning spin, and he predicted that if you actually inverted the spin of an atom, if this were to happen in nature, that it should be detectable as a really long wavelength change. So the wavelength is actually 21 centimeters long, so it's called the 21 centimeter line. It's a pretty long, I don't know how long 21 centimeters is, but it's a pretty big wavelength of light, actually. And it turns out to be this is the case, right? And they actually were able to look and find this 21 centimeter light. And it turns out that that's used as the announcement of the presence of neutral hydrogen. Now, spin's a really, really abstract, bizarre concept. I think that I've touched on this a little bit before, but I want to make sure that we're really keen on what this actually means. So, spin in quantum mechanics, with respect to an electron, we say an electron has a spin 1/2. The spin 1/2 means that that electron has to rotate around twice to get back to its starting point, which is a really, really bizarre thing. This is how it's illustrated on Wikipedia, actually. Now, since it's such a bizarre symmetry, having to rotate twice to get back to its starting point, most, let's say nearly all quantum mechanicists, I hate calling them quantum mechanics. They sound like they're working on cars or something. But quantum mechanicists, they would say this is just an abstract concept, but it's not something that you can actually visualize, which I think is a little bit of a cop-out personally. Spin is actually, in the quantum mechanical equations, it tells us about the intrinsic angular momentum of the electron. Now, the electron is the outer surface of a hydrogen atom. There's no doubt about it. It's how the chemists have understood it for hundreds of years, 150 years. So what in the heck is going on with the momentum of the shell of the atom such that it can rotate around twice to get back to its starting point? I think that a really good way to visualize that, and hopefully this will play, is that the shell itself is indeed spinning around the equatorial axis of the atom, but it's also involuting in and rotating down through itself and back out like this. Right? So if you can imagine the shell of the atom is going inside and coming out the bottom, then what I've done here is I've made a model for what spin 1/2 can look like for a hydrogen atom, right? Surface is going in and out. Now, I'm not saying this is the case, I'm saying this is a actually reasonable mechanistic way of looking at what this concept of spin is going on. So if you have a spin flip inversion, what are you doing? Well, you're turning the pole of the atom in the other direction, essentially, the electric pole of the atom. So it's almost like AC current. You're flipping the orientation of the pole of the atom. This is another, hope this will play too. This is kind of a similar process. Have you guys seen this before? I'll talk about this in a second. So when an object has a slightly off-center of mass and you rotate it in outer space, it will build up that instability over time, and periodically its pole will invert like this. This is just a natural phenomenon that happens because of the fact, if we can play that again. Okay, now the funny thing is, this was discovered by the Russians back in the Cold War. And they weren't really on speaking terms with the United States. Well, it turned out they were actually just like somebody was adjusting a wing nut on something at one of the space stations, and it flew off the handle kind of like that. And it started doing this. And the guy was a scientist, and he freaked out because he thought, oh my God, this is going to happen to the Earth. Right? And so they sat on it for 10 years because they didn't want to panic people about it, actually. Now, most people aren't worried about that happening to the Earth today, but it's an interesting experiment, right? The idea is that because this thing has the wing nut has a very serious off-center of mass, right? It has the stick hanging out of one end that it might flip over like that. The Earth doesn't. However, various proposals have been lodged prior to this concerning the ice caps being sufficient as to pull the spin axis slightly off of its center of mass, which would, of course, result in the whole thing flipping over. No one's ever seen this happen to a planet before. People don't seem to be worried about it, but the Russians were absolutely terrified they were going to start World War III if they let this experiment out of the bag. So that's a really funny experiment. But I guess what I'm trying to propose is that I think that a reasonable way of thinking about spin flip as well with the atom is something like this as well, right? And I think AC power might be something kind of like this as well, where the direction of the pole of the atom, the shell, the pole of the shell is turning from side to side. So I hope that helps you guys visualize that a little bit better. Okay. So this is the picture of the guys with their big telescope who first detected this 21 centimeter line. Let's just go ahead and put a pin in it here, and next time we'll talk about the ultra hot ISM, and we'll continue with all of this. It's a good place to stop. Have a good week, guys, and I'll see you. Hey, let's do coffee on Thursday if anybody wants to come. I'll be here, 8 a.m.